This video will take a quantum deep dive into magnetism, moving beyond the simple concept of north and south poles. We see magnets every day, but the mechanism is a complex interaction of atomic lattice structures, quantum spin, and virtual particles. The standard high school explanation uses field lines, showing lines flow from north to south. This predicts behavior but fails to explain the physical mechanism. To understand the why, we must zoom in past the metal bar, down to the atom. The source of magnetism is the electron. In the classical model, electrons orbit the nucleus, and moving charge equals magnetism. However, if every atom has orbiting electrons, why isn't everything magnetic? This leads us to the quantum model. Electrons possess intrinsic spin, a fundamental quantum property that carries angular momentum. The orientation of this spin determines the direction of its magnetic field. While they don't physically rotate, every electron acts as a tiny bar magnet. In most materials, electrons spin randomly, causing random cancellation and zero net magnetism, as seen in wood or plastic. In ferromagnetic materials like iron, large groups of electrons align their spins locally, forming, quote, magnetic domains. Magnetization aligns these chaotic domains. The Pauli exclusion principle, which states no two identical fermions can be in the same state, dictates why electrons align or pair up. To get magnetism, we need unpaired electrons interacting across atoms, as paired electrons with opposite spins cancel their magnetic fields. A material becomes magnetic through exchange interactions. Following Hund's rule, electrons prefer to singly occupy orbitals. In materials like iron, electrons on neighboring atoms align spins parallel. This alignment keeps their wave functions further apart, reducing repulsion and creating a lower energy state. We know magnetism is generated by aligned spins, but how does the force transmit across empty space? Quantum electrodynamics, or QED, explains that the force is mediated by virtual photons, which are excitations in the quantum field that carry the electromagnetic force. Virtual photons are the messengers of force. Repulsion is like tossing a heavy ball back and forth, creating pressure that pushes objects apart. Attraction involves a complex momentum transfer, similar to exchanging boomerangs, which draws the objects together. At the fundamental level, particles are waves. Attraction occurs when opposite poles approach, and wave functions overlap constructively, creating a stable, lower energy state. Repulsion occurs when like poles clash, creating destructive interference, a high energy pressure state that pushes the magnets apart. The quantum synthesis of magnetism starts with intrinsic electron spin, which is aligned by quantum rules in the atomic lattice through exchange interactions. This forms macroscopic magnetic domains. The force is mediated by virtual photons, and attraction is the system seeking the lowest energy state through constructive wave function overlap. What seems like a simple attraction of metal bars is actually a symphony of quantum mechanics, involving spins aligning, exclusion principles dictating traffic, and virtual particles bridging the void. The universe is indeed deeper than it looks.